So Nikolay will present the joint work with Alexander Mikhailovich Tarasyev, which is entitled Mechanism for Dynamic Shifting of Antagonistic Equilibria to Cooperative Solutions. We can, I believe that we can wait a few minutes now. Hello, Vanessa.
Hello. Sorry, I had some technical issues. So,
all is okay. We didn't have any problems, so just.
Vanessa, is there a storm where you are also?
No. It is not that technical issue. No, it's okay. The weather is just fine now.
Vanessa is in another part of Russia, in the south.
Ah.
We are in the west north.
You are in St. Petersburg? Where are you?
I am in St. Petersburg, but Vanessa, no.
And what's the name of the area where Ovanes is called? What's it called?
Sochi. Sochi. Sochi is on the south of Russia. It's where the Olympic Games took place, the Winter Games, if you remember.
Yes, I will look on the map more carefully afterwards, but good to know.
Yeah, it's just on the south. It's a small city, but you know.
I see.
Okay, maybe we can start.
Yeah, now we start. I already announced the talk, so just please.
Thank you very much, Ekaterina, and thank you, Vanessa, for the organization of such a great conference. And I would like to, my name is Nikolay Krasovsky, and I would like to present a paper called Mechanisms for Dynamic Shifting of Antagonistic Equilibria to Cooperative Solutions, developed by me and Alexander Tarasyev, and we are from Krasovsky Institute of Mathematics and Mechanics from Yekaterinburg, Russia. So as an introduction, we consider a model of evolutionary non-zero sum game between two groups of players in the framework of differential games. We present mechanism designed for constructing value function and guaranteeing strategies which shift players from antagonistic equilibria to cooperative solution. We also construct the dynamic Nash equilibrium feedback strategies of players maximizing their own payoff functions. Resolving strategies provide better results as compared to classical models of evolutionary games, for example, models with replicator dynamics or static games. So here's the outline. So in the analytical framework, we present game dynamics, payoff functions of coalitions, interests of coalitions, dynamic Nash equilibrium. Then we present solutions to differential games and modeling example. So we consider two groups of players, and each player can choose between two strategies, first or second strategy. Behavioral dynamics of coalitions are subject to control from Magorov differential equations. Here, X is probability of randomly chosen player from the first group taking the first strategy. Y is the probability of randomly chosen player from the second group taking the first strategy. U and V are control variables. For example, U equals 0, V equals 0 means change first strategy to second. U equal 1, V equal 1, change second strategy to first. U equal X, V equal Y, keep the previous strategy. We consider two matrices.
So you don't allow players to choose mixed strategies for some reason?
Yes, we don't allow them to do that.
Okay.
We consider two matrices, A and B. So A is payoffs of the first coalition, B payoffs of the second coalition. Indices of elements correspond to strategies of players. For example, A11 is payoff of the first player in the situation where both player takes first strategy. For example, B12 is payoff of the second player in the situation when first player takes first strategy and the second player chooses the second strategy, and so on. Payoff functions of coalitions at time moment t are determined by expected payoffs in the Bimatrix game. Interests of coalitions are determined as double-valued functions formed by lower and upper limits of expected payoffs. Dynamic equilibrium is based on solutions of zero-sum differential games. Equilibrium trajectory is constructed using guaranteeing feedback strategies of coalitions when each coalition maximizes its payoff functional. Strategies maximizing payoff functionals of the opponent are called the punishment strategies. So here's the definition of dynamic Nash equilibrium. Here, a pair of feedbacks U0, V0 is called the Nash equilibrium for an initial position X0, Y0 if for any other feedbacks U and V, the following condition hold. These inequalities are valid for all trajectories. And here symbol X stands for the set of trajectories which start from initial point and are generated by corresponding strategies.
Can I have a short question? How dynamic Nash equilibrium is different from classical definition of Nash equilibrium for differential games? Because I see epsilon, it's kind of epsilon equilibrium,
yeah.
Right? Or no?
Yes.
What is the key point?
Yes, it's another definition of this equilibrium is epsilon Nash equilibrium.
Okay.
So dynamic Nash equilibrium, here's the explanation. It can be constructed by pasting positive feedbacks and punishment feedbacks according to the following relations. First, we constructed value function and differential game with fixed terminal time t. By that, we solved the game with dynamics 1 and terminal payoffs JA and JB. Second, we constructed value functions for the game with dynamics in equation 1 and with the following functionals. We proved that constructed value functions solve the differential game on the infinite time horizon, the initial game with interest of coalitions. Let us recall that here JR and JB are expected values determined earlier. We proved that there exists a saddle point which determines the stationary value function. Here trajectories are generated from initial position by feedbacks U and V of maximizing and minimizing players respectively, and by the arbitrary controls of their opponents. Here on this figure, we present the structure of a value function WA for the first player. We depict domains EA in which the value function is given by smooth components. On the lines KA1, KA2, KA3, KA4, and KA5, continuous pasting of these smooth components occurs. Non-smooth pasting takes place only on lines KA2 and KA3, on which the inequalities for the conjugate derivatives of the value function are verified. Let us know that it is these lines that define the synthesis of the optimal control strategies of the first player. We derive feedback control strategies using the value functions. Here also we prove the theorem that the intersection of sets E4 and A4 and B4 is non-empty, and hence optimal strategies UA and VB generate trajectory that enters intersection E0 and stays there on the infinite time interval. Here we present the synthesis of the optimal control of the first player, which is given by switching lines KA2 and KA3. These lines divide the square of game position into two parts. If the current state of the trajectories is in the left part of the square, then the control of the first player is U equal 1, and the motion occurs from left to right. If the current state of the trajectory is in the right part of the square, then the control of the first player U equals 0, and the motion occurs from right to the left. The direction of motions for the first equation of the dynamics is indicated by arrows. Here's the example. We model a game with one static Nash equilibrium. Let us consider a game of stocks and bonds on the financial market. Matrix A describes behavior of traders who play an increase of the interest rate and are called bulls. Matrix B describes behavior of traders who play on decrease of the interest rate and are called bears. Matrix parameters mean profitability of stocks and bonds expressed as interest rates. Interest rates data is taken from the US Stocks and Bonds website. Here's the final picture. Here we present the point of static Nash equilibrium, switching lines KA and KB of player strategies. These switching lines set the directions of controls, and namely, broken line KA says the change of control for the first player in the direction left to right or right to left. Line KB says the change of control for the second player in the directions down to up or up to down. Trajectories generated by guaranteed strategies are depicted by symbols T1, T2, and T3. They all start from different initial points I1, I2, I3, and all converge to the intersection point of switching lines, which we call ME, or market equilibrium. So here we see that, for example, if trajectory starts here from the point I1, the direction for the first player goes from left to right, and for the second player goes from up to down. So this trajectory is directed to this vertex of the square. When it changes the line, the sliding mode occurs, and they all slide to this point. And calculations show that the values of players' payoffs at this point of market equilibrium are better than at the point of Nash equilibrium. Here's the table, which shows that mean values for this payoff functionals are much better than in static Nash equilibrium. So as a conclusion, I would like to say that notion of the dynamic Nash equilibrium is analyzed for the Bimatrix evolutionary games. Basing on the maximizing strategies, the computational algorithms are developed for the construction of equilibrium trajectories. We proved that obtained trajectories provide the result for payoff functionals of players better as compared to values of the static Bimatrix game. And for the future research, we are planning to increase the dimension of Bimatrix games to the dimension 2 by 3 for solving the dynamic version of well-known matrix game rock, paper, scissors. So that is all. Thank you for your attention.
Let us thank the speaker. Okay, thank you very much. So, any questions?
I have a question. Can you please explain the example once more? One of these two pictures, could you explain in details what is it? Is it yeah, for example, what is the point NE? This is the point where the strategy will converge, right?
No, point NE is a static Nash equilibrium, so it's for the static game. And the point ME is where these three trajectories, they all converge by sliding on the switching lines, and they all finish on infinite time horizon, and they all finish their motion here on this point.
Okay, maybe I don't understand. So what this figure actually presents? What is the meaning of this figure? What is the point in the figure? How to understand it? Maybe for some it is clear, for me not.
So this shows how the synthesis of this dynamic Nash equilibrium is working. So we choose any initial position in the square 1, 1, and we start trajectories with the dynamics that was recalled in the beginning.
Yes.
So all these trajectories, they all start their motion for different vertex of the square. For example, this goes here, this goes here, this goes here, and these switching lines, they switch the motion of the trajectories. So when this trajectory approaches the line Ki, its direction must change according to the dynamics, and when it goes here, then it's approaches the line Ka, and it appears in this area. So in this area, it should go in this vertex, because the dynamics direction will show it to go from right to left and from up to down. So it goes here, and they all finish here.
So it's a kind of figure with the initial positions, right? Initial conditions.
Yes, and we can choose any initial. We can choose any initial condition, and we show that they all converge to this point, which is has the values for the payoffs of players are better than in static statement.
But what is the cooperative framework here? I didn't get it. Yeah. We can show, I did mention this in this paper, that this market equilibrium, it possesses cooperative properties, because this Nash equilibrium is non-cooperative. We can find it when each player maximizes its own functional, doesn't depend on other player, and so we also could start, for example, from here, also from Nash equilibrium, and it still will go to this point. And this point possesses cooperative structure, and the values of player functionals are better in this point than in static Nash equilibrium.
Hi, Nikolay, this is Andrei. If I may add, maybe what you ask is also some interpretation of this X and Y. So if I remember correctly, it's just some fractions of each coalition which follow one of the strategies. So maybe initial conditions show that one coalition is more taking strategy 1 while another strategy 2. But in a dynamic equilibria, they converge, as we see, to the quite different values. For example, 0.1 for X and around 0.25 for Y. So what does it mean in this situation? Is it that there should be more bulls or bears? How it is interpreted?
Yes, bulls or bears, bulls for X and bears for Y. It's their profit, interest rates. It's their profit.
How they could cooperate, these two different groups? So I didn't get it.
Because these equations, as Nikolay showed in the beginning, as I saw them, they are coupled. So they're coupled through controls. It's not only that you impact your dynamics, but you can also impact another coalition. Therefore, they can maximize the joint benefit.
I see. Okay. Other questions?
Yes, I have a question. Can we try to control the system somehow to make so that the Nash equilibrium would converge to market equilibrium, or to make Nash equilibrium Pareto optimal, or this kind of thing, or it's not the point. It's not very interesting.
This dynamics is just like a natural behavior of players. So it just describes how they behave naturally. So that's why how it happens when.
Now, Nikolay, I think if you go to this figure, the question is that if you start from Nash equilibria, I think it's just not shown here, but of course you will also converge by controlling the system to the market equilibria. So this works for any initial condition, including static Nash equilibria.
Okay.
But
Okay.
what is the best strategy here? To be bear or to be a bull?
Classic question.
So it is shown that for bulls it's almost the same in different points, but for bears it's better to stay in our new market equilibrium, because in Nash equilibrium we have a very low income.
Yeah. Okay. Thank you again. Any questions or comments? If there is no, we will ask the next speaker to be prepared to his talk.
Can I ask last question? How the payoff function looks like? It is the integral, right? But which integral function for which interval?
Now payoffs function of the players are shown just like as expected values.
The matrix.
The matrix game, yeah, it's like this. So we just put final x and y in the equation and get the number.
Okay. Thank you very much. Thank you. Okay, I will not take more time.